Thank you, Danny, and thank you for inviting me to give a talk here in this special symposium. I first want to start with, again, congratulating our prize laureates. Neil, of course, that is sadly no longer with us, Shri and Andre. And I want specifically also to thank Shri, who has a big role in actually bringing me here today. He was my advisor at Caltech when I did my postdoc there, and introduced me to the very intensive time domain field in the world of PTF, the Palomar Transient Factory. And also under his wings, I became a radio astronomer. So I started leading the radio follow-up observations of the Palomar Transient Factory program. So I'm going to talk about the future of radio astronomy, basically what we're going to do, what we're doing now and next, since the future time domain was selected as a field in the Dan David Prize this year. But we cannot start talking about the future before talking about the past. This is where things began with Shri. If you recognize him here, Shri, where is that taken?
At Creek.
At Creek, okay. So this is the technology that was available when Shri was a student. And thankfully, we advanced since then into the future. And we're using this brand new facilities and facilities that have been with us for many years and are going through upgrades. So you all know that time domain field have been going through a revolution in the last decade thanks to the optical surveys like PTF, PanSTARRS, SkyMapper, the upcoming BlackGem project. And in the radio, we've been lagging behind a bit. And thanks to technological advancement, we're really making steps into the time domain field as well, into the future. The VLA, the very large array that you see here, a veteran facility has been upgraded, giving it increased sensibility and new capabilities. And you see this all across the radio spectrum. If you go to the lower frequencies, like megahertz, you see these stations across Europe. Those are the LOFAR stations. We have these kind of low frequency arrays in the United States. Caltech is actually building one led by Greg Hallinan. There is one in Australia, the MWA. If you go to the other end of the spectrum, into the millimeter range and the sub-millimeter range, you have a brand new facility, which is about 5-6 years old now, ALMA Observatory, that really revolutionized the field of millimeter observation. This is $1 billion observatory. So there is a lot of investment, also financial investment on a worldwide scale, actually, in radio astronomy nowadays. And that enables us to do great things in time domain. Just a few other words about some other facilities. The AMI facility, this is a telescope, an old telescope in the UK with a new capability of rapid response. So it's been upgraded, giving it new sensitivity thanks to a new correlator. But also, so far we know that the Great Swift Observatory that Neil led gave us great science on gamma ray bursts, and on the ground, optical telescopes flew immediately to the position of the GRB when it was detected by the satellite, and now we can actually do that with radio telescope. This telescope can go into the position of a GRB and observe it within a minute. So we have rapid response capabilities now also in the radio. We have brand new facilities like Meerkat, that is a pathfinder for the square kilometer array, ASKAP in short. You can start seeing the dishes just popping out on the ground, and this will be commissioned this year, this full array with all the extra dishes. And there will be a 5-year project in time domain called Thundercat on this telescope that I'm part of. Another pathfinder for SKA is the ASKAP telescope in Australia. And this is a truly survey machine, thanks to this detector, which gives us a large field of view of 30 square degrees. And if you think about it, what we heard about in ZTF, really increasing the field of view to above 40 square degrees in the optical, we're now doing that in the radio. So we can start actually doing large surveys in time domain directly in radio wavelengths. And of course, down the road, we'll have the square kilometer array, which will really revolutionize the field of radio astronomy as a whole and also the time domain field. So let's go talk about the science that we're doing. My focus is about supernova, or the death of massive stars. And we all know the regular story. You have a massive star forming. It goes through some evolutionary path. Different evolutionary paths exist. It can end up as a compact Wolf-Rayet star, as a super red giant, something in between. Eventually, it will collapse as and explode as a supernova. And we study those. And we hope to, through the study of supernova, to learn something about massive stars and their evolution, and learn about the physics and the processes that led to the explosion. Basically learn something about the last stages of stellar evolution. So this is the story we all know, and radio really provides a unique aspects in studying this type of supernova and their progenitor stars. It can tell us something about the interaction of the supernova ejecta with the environment, tell us the velocity of the ejecta, of the fastest component that is sometimes hidden in optical wavelengths. From that, we can learn something about the progenitor size, maybe about the density structure of the progenitor star that exploded, about the mass loss history of the star just before explosion, which is a key ingredient in stellar evolution, really. Just to show you a classic example, and in the recent years and also nowadays, what we're mainly doing is studying individual objects. So a classic example is supernova 93J, an old one. Very nearby, you can see this terrific optical light curve, a type 2b supernova. And this is those extraordinary radio light curves that you get when a supernova goes off very nearby. You can see this in different wavelengths, actually, and you can model that and get some physical parameters. Because it's very nearby, you can also do VLBI measurement with high resolution and resolve the shock wave as it evolves and measure the velocity of the expansion. As I said, you can measure the mass loss, which is very interesting here. It's not a regular mass loss. It peaks somewhere and then decreases just before explosion. So you have to explain this behavior somehow in those stellar evolution models. Okay, so what do we know about this supernova, for example? We know that it's a K-giant star from archival HST images. We know that it has varying mass loss during the last 10,000 years. And the initial shockwave velocity, the fastest ejecta, is about 18,000 kilometers per second, eventually decreasing over 1,000 days. Okay, so we have to explain this with stellar evolution codes or models. How do we get this kind of mass loss and progenitor properties? The most common explanation nowadays for this type of supernova is that it's coming from a binary system. The mass loss is a result of a mass transfer due to the existence of a companion. And there's actually clues nowadays for this specific supernova that a companion indeed has been identified with HST late-time images. Just to show you that we're still doing this kind of work, this is a PTF discovery, supernova 11D age, discovered early on. And since we discovered the supernova early on, a day after explosion or a few days after explosion, we can get again these beautiful light curves in the radio, okay, in different frequencies. And we can get the shockwave radius and its evolution with time and the evolution of the magnetic field. For this object, for example, we got the earliest millimeter observations of this type of supernova. Again, like 93J, we can actually measure the velocity of the fastest ejecta, and it indicates an intermediate sized progenitor. And specifically what I want to mention for this supernova, that the importance of also of combined analysis in different wavelengths. In this case, we had observations from Swift, from the VLA, and also from optical observatories, which enable us to do a combined analysis and actually test some assumptions that we usually make. And in this case, we found, for example, that the assumption of equipartitions is not valid. There is large deviation from equipartition. There is a lot more energy in the electrons that emit the synchrotron emission than in the magnetic field that is formed at the shockwave front. So this is what we're doing now. What we should do next? We should really move to study unexplored phase space. And how should we do that? We should move beyond studying individual events in detail to studying large samples of supernova on different timescales. Why should we do that? If you look at this panel, that shows you the top panel shows you the peak time in the radio light curve for different parameters like different mass loss rates, different shockwave velocities. You can see the peak time can vary from a day or a few days until hundreds of days. So sometimes we do a bad job at observing supernova. We observe early and stop, or we observe late and stop, and didn't observe at the beginning. So we miss all these peaks. Okay, so we have to be diligent and do our work well and have a large sample observed from the beginning, a few days after explosion, till late time. Some actual events that show that. Let's look at the short timescales first. This is PT of 12 GZK, okay, detected after a few days after explosion, had a radio detection and then it faded away quickly. There are two other supernovae that are known to do that. Those are fast radio supernova, which emission goes away within a week or two. After a few days, the emission at low frequencies already is diminishing. Those are type 1c supernova with intermediate velocities about 60,000 kilometers per second. The normal type 1c supernova have shockwave velocities of about 0.1 c. We know of the relativistic ones that have relativistic velocities that are associated with GRBs, of course, and those are intermediate events, okay? And this is highly unexplored population. We only know of a few events. The new capabilities of telescopes, radio telescopes, allow us to observe this at 58 megaparsecs. Those two events were observed before that within 10 megaparsecs. So we now have the capability, the early detection, and the increased sensitivity to actually go and do that. Some other examples, we know that sometimes stars just eject massive shells of material prior to explosion, as we heard before today. This is just one example. There is a precursor in the optical light curve before the supernova goes off here. This is from a paper by Ran Ofek. And the interpretation here that indeed the star just burped and ejected a lot of mass prior to ejection, creating a CSM shell very nearby to the star. We see this, as Avishai presented in his talk, also in flash spectroscopy supernova. When you detect supernova very early on, a few hours after explosion, and observe it a few hours after explosion, or maybe a day or two after that, we see these high excitation lines that disappear after a few days. The explanation here, or the interpretation here, is that again you have a CSM shell, a dense shell, which is thin in size just outside of the star. And the stellar ejecta moves and sweeps this CSM shell, which we see as a signature in the spectrum after a few days, and this is why actually the lines disappear. We heard about this in Avishai talks. I won't go into too much detail. There's also a question whether there's also a low density extended CSM. Now, to confirm this interpretation, what we want to do is actually see signs of interaction of the stellar ejecta with the CSM shell itself. The way to do this, if you just look at the predictions for this type of object that we observed so far, is that those are the predictions for the radio light curves. The radio emission will cease after a few days. And this is our current detection limit around here with the different telescopes. So we can only do this in high frequencies. So we cannot do this with the VLA, but we can do this with the brand new telescope ALMA in the millimeter range. And this was not available before. This is just now available to us. We just submitted a proposal to do that. I hope it gets accepted and we can actually test this assumption. Let's look at the long timescales. And if you look at long and late time light curves in the radio, like in this supernova 79C, you see this sort of wiggles. Those were interpreted as having a complex CSM structure around the progenitor star, this spiral structure. How do you get this? If you have a star losing mass and it's in a binary system, it does this kind of a motion, then you get this spiral structure. Okay, so if you detect this kind of spiral structure, it might also give you an indication that you're observing a binary system. We actually see this kind of systems in nature. This is a real image from ALMA showing Alpha Scorpius losing mass. It has a companion, and because of that, you can have that spiral structure. Okay. Last example of what we should observe at late times. This is supernova 2014C, detected initially as a type 1b supernova, a supernova that lost all of its hydrogen envelope. And then it evolved over 100 days into a type 2n supernova. You can see the age alpha emission line just picking up over 100 days, becoming a type 2n supernova. And if you look at it in the radio, this is what you see. Weak radio emission at early times, almost just above the host emission in the radio, and then it's just picking up, becoming very bright in the radio, peaking at 70 days, falling, and then it picks up again to even a brighter luminosity in the radio. This is at 400 days, at 15 gigahertz. You usually don't see these kind of things. And there is a question whether it's something unique or something that we just miss because we don't observe that late. Maybe it's something that happens a lot. So this is another indication that there are shells or maybe clumps that don't necessarily have to be on the same, even the same line of sight, that just lie far away from the progenitor star and were sometime ejected from the star itself before it exploded. Okay, moving on from just the death of massive stars and what we should do with large statistical sample in the near future, we can also study new and rare transient classes and new phenomena. We have some promising events that are promising for the future. This is one example, PTF11AGG, a fast optical transient, just appear one night and decreased by a few magnitudes over the night. And it has a long-lasting radio emission that just faded over months and scintillated. From the scintillation, you measure the expansion velocity, and based on that, we found that it's actually a relativistic event with a mild relativistic Lorentz factor of just above 1.5. You may ask, what is this? We usually see this kind of thing from long GRBs, but searching into the high energy archives of all the high energy satellites, we don't see any high energy emission. Okay. We don't know exactly.
Dispersion measure?
No. So Brad Sanko led this paper. It was here on Sunday. Did all the calculation. What is the chance that this was a GRB? What we just missed the high energy emission. There is a chance for that. It's a low probability chance, 2% chance that it's actually low luminosity GRB and we just missed the emission. But given that low probability, we really have to consider other alternatives. So maybe it's a new type of relativistic explosion that doesn't exhibit or doesn't create high energy emission, maybe a dirty fireball. So certainly this is a motivation to pursue these kind of things in the future, and the radio provides a lot of the information here. We also study rare classes like ultra-long GRBs. We don't know a lot of them. They are rare. They occupy their own phase space here in this phase space of luminosity and time. They have prompt emission in the gamma rays above 1,000 seconds and up to 10,000 seconds. They show flaring in X-rays on the timescales of 10,000 seconds, not like long GRBs that just falls off like a power law. And people suggested that maybe those are tidal disruption events. Maybe they're just the collapse of extreme extended stars. Who knows? And we have only one detailed early radio observation of this type of object. This is it. And it shows peculiar emission already 2 days after detection, which is what you see here. Those are just two different fits for different functions, Pauli distribution, and monoenergetic distribution for the emitting electrons. And first thing that you notice is this, after 2 days, the peak is below 10 gigahertz, which suggests a high CSM density, which is in contrast actually to what the X-ray data suggests here. So this is a mystery. And more surprising is this cutoff, this steep cutoff here, around 8 gigahertz, which really gives you a very steep Pauli distribution or a monoenergetic distribution, something that you don't see in normal long GRBs. And there is a question, how do you create this kind of energy distribution for the emitting electrons? What is the acceleration mechanism responsible for that? Another hot topic is tidal disruption events. They have been known for a while, but we're discovering more and more of them. The onset of relativistic TDE was only made a few years ago in 2011. This is Swift J644, so another discovery by the Great Swift telescope. So you see here the X-ray, actually the X-ray light curve, and also again, radio light curve provide the important information here. It actually helps associate the emission with the nucleus of the host galaxy, again, indicating it's indeed a tidal disruption event of a star by the supermassive black hole at the center of the galaxy. It provides some information about the energetics. It confirms that it's a relativistic event. And also, it provides the Lorentz factor. And if you look at the light curve, it's kind of strange. You see that it's rising, and then it's flattening out, and then rising again. Now, some people interpret that as having multiple components with multiple Lorentz factor ejected. Some people suggest, like Tzvi Piran, that actually there is a strong process of inverse compound involved early times, and that goes away at late times, giving rise to the radio emission, and this is why it becomes brighter again. Also, a recent result, we have I mean the community, have seen the first radio detection from a thermal TD. Those are non-relativistic. The radioluminosity of those is much fainter than Swift J1644. The velocities are small. You can see about 12,000 kilometers per second. We have these beautiful light curves. This is from Kate's Alexander paper. And there is a question, what do we see here actually? What are those outflows? Where are they coming from? Is it just outflows from the accretion disk here around the black hole? Or do we see the unbound material of the star going outwards interacting with the ISM? So these are some of the suggestions. It's still unanswered. Since this is the first object, we hope to find more of this in the near future and study this in more detail and have some answers, hopefully. Moving on to the future, really having two types of transients that are really exciting, and I think everyone is looking forward to see what's going to happen with them in the near future and the far future. The first one, of course, is gravitational wave counterparts. So the greatest discovery of this century was, of course, the first detection of gravitational waves by the LIGO team. You can see here the signal that was detected, and this is indication of a compact binary merger, in this case, two black holes merging. We hope to find also mergers from black holes in neutron star or neutron star with a neutron star. And those are actually expected to give us some electromagnetic emission. What do we expect to see in those cases? First, we expect to see a short GRB. So we believe short GRBs are related to those compact binary mergers because there will be those jets emitted, creating this short GRB. Also, all the models show small amount of material ejected, about 0.01 solar mass. This will be radioactive and actually will give you emission in the optical and IR. This will be a very weak emission on timescales of a day to a week. Okay, this is sort of the range that you get from what is presented nowadays in the literature. And eventually, Tzvi Piran and Udi Nakar wrote a paper about the expected radio emission from this type of object. You should expect this ejecta to interact with the ISM, giving rise to radio emission. Okay, so if you look at that paper, you expect weak emission on sub-millijansky, I would say, levels. The emission will peak on timescales of years, and this is highly dependent on the properties of the event. The kinetic energy of the ejecta, the ISM density, the microphysical parameters. And we're certainly looking forward into the future and trying to detect counterparts also in the radio of future LIGO detections. We might have to wait for the bulk detection, really, we might have to wait to the SKA. Okay. We might not have the right sensitivity to actually make those discoveries just now. Maybe for 1-2 events, who knows? We really don't know what are the properties of these events. Right now, we can already start constraining the phase space of these events by actually looking directly at short GRBs, which are, again, the result of these compact binary mergers. This is just an example of constraints we got on the phase space from observations, late-time observations of two events that are short GRBs and also show the macronova signal. So they have the two first signals, the GRB one and the IR one, but they don't have radio emission. This is late time. We don't detect anything. So we can actually put constraints, which is what you see here in as solid line. Everything here above that solid line is ruled out. The phase space here is kinetic energy, the ISM density, and different physical, microphysical parameters. This epsilon B, and this is for one event, and this is for another event. Actually, one thing that you can rule out here is the magnetar scenario, which is if you form a magnetar in the merger, this is what you expect, the dashed line. Also, what you should consider if a magnetar is formed in some of the cases, another contribution by Shri. This is a work of Shri and Tony Pyro. They suggest that if a magnetar is formed, you may expect Plarian emission from a pulsar wind nebula, and this will peak on timescales of months, and this does not depend on the ISM density. So this should be quite bright and detectable. So this is one class that is very exciting, and everyone is looking forward to see what we're getting. And another thing that is not related to this kind of explosion or slow transients, as people refer to them, those are the fast radio bursts. These are events that occur on timescales of milliseconds. So we're usually using totally different telescopes to observe them, single dishes that usually used to observe pulsars with great timing resolution. Of course, it was detected in the past as the Lorimer burst, but then really the community got excited again after a sample was discovered by Thornton, and now people know of more of them. I think there are about 20 or 30 FRBs known right now, and they raised a lot of questions. This is a true mystery. Until recently, we didn't know if they're cosmological, galactic, terrestrial, what is their true rate, what is the progenitor, are they coming from cosmic explosion, are they coming from stars in our own galaxies, maybe active stars, do they have some exotic origin like cosmic strings? There have been a lot of papers and a lot of theoretical papers on the subject. This is just showing you one of the events which is dispersed in time and suggesting that actually this is an event that comes outside of our galaxy. And indeed, it was recently confirmed, the first FRB, which is a bit different from the other FRBs because it's repeating, it's a repeater, was localized by the VLA at a host galaxy, which is a dwarf galaxy at a redshift of 0.2. So we now know of the first FRB that it's outside of our galaxy. I think, Shri, this is where you really lost your money on the bet. So Shri lost $1,000 for those of you who don't know on this. To Paul Hood. We have a picture of him if you want. He paid him by $1 bills. So there's a lot of advancement also on this front, which is very exciting. The whole community is excited about it because this is a true mystery. We don't know almost anything about this kind of thing, but we keep seeing them with different telescopes. And people are really devoting a lot of resources in studying this type of objects now. Shri is leading a collaboration or an effort in the Owens Valley in California to build a small array specifically to detect this kind of events called the DSA, Deep Space Array Telescope. Which you see here, there is the CHIME telescope being built in Canada. There is Utmost project in Australia. All of this is dedicated specifically for FRBs. So I want to quickly summarize after giving this really overview of things we can study in time domain in the radio and what's the importance on radio, what its contribution, and what should we focus on in the future. First, in the study of supernova, core collapse supernova, or the death of massive star, we really should move on to study large statistical samples, let's say up to 100 megaparsec of different types from day one until a few years after explosion. We can start going forward beyond just studying the CSM, which is just spherical as we see usually from wind structure around stars, and we can identify complex structures of CSM, including shells. Moving on to the rare and new classes, we can study fast optical events, we can study ultra-long GRBs, we can study nuclear transits, and always in time domain surveys, there is some room for unexpected surprises with new types of transients. And also, I want to say that really the icing on the cake will be to identify the gravitational wave electromagnetic counterparts and really to solve the FRB mystery. And with that, I think that really we should look into the future and understand that the future is really bright, and I'll end with that. Thank you.